Hey there. Ever wonder why a single pixel in a photo can trick an AI into seeing a completely different object? Or why self-driving cars need to be super reliable? The answer lies in something called Lipschitz constants, a math concept that's actually simpler than it sounds. Let's dive in. Think of a neural network as a complex recipe. Each layer transforms data step by step, like ingredients in a dish. But here's the catch. If the recipe is too sensitive, a tiny tweak, like a single pixel shift, could flip the whole outcome. That's where Lipschitz constants come in. They measure how much the final result changes when inputs are slightly altered. A low constant means stability. A high one means the network is as skittish as a nervous horse. But here's the twist. This study isn't about trained networks. It's about random neural networks, those initialized with random weights like a blank canvas. Why? Because understanding these untrained systems reveals the mathematical foundation of deep learning. It's like studying a blueprint before the building is constructed. The focus is on ReLU networks, where neurons only activate if inputs are positive. Researchers asked, what's the Lipschitz constant of such a network and how does it change with depth or width? Their findings are wild. For different values of p, which defines input change measurement, the Lipschitz constant behaves in surprising ways. When p is between 1 and 2, it acts like the Euclidean length of a random vector. But for p greater or equal to 2, it mimics a more complex statistical property of random data. It's like the network's sensitivity shifts gears depending on the rules of measurement. Now here's the kicker. For shallow networks, the math aligns perfectly. But for deep networks, there's a tiny logarithmic gap between upper and lower bounds. However, this gap shrinks as the network gets wider. Great news for real-world applications. How did they prove this? They combined two powerful ideas. 1. Gradient analysis. By studying how outputs change with inputs, they estimated maximum sensitivity. 2. Random geometry. They used techniques from random hyperplane tessellations. Imagine slicing input space into regions to analyze how networks partition data. The paper's real magic. It bridges zero bias and general networks. Even with non-zero biases, the insights from simpler models still apply, though with some adjustments. It's like learning to ride a bike with training wheels, then graduating to the real thing. So why does this matter? This research isn't just math, it's about building smarter, safer AI. By understanding sensitivity in random networks, engineers can design systems that stay reliable, even with tricky data. Whether it's a medical diagnostic tool or a robot navigating a factory, this math ensures the AI stays calm, cool, and collected. Next time you interact with AI, remember, behind the scenes, math like this keeps things from going haywire. Thanks for watching. If you want more deep dives into the science of AI, hit that like button and subscribe. Until next time, stay curious.